When a super tall skyscraper sways in a storm, most people assume the structure is failing. In fact, the opposite is true. That movement is the foundation doing exactly what engineers designed it to do. The way modern skyscraper foundations handle wind forces is one of the most sophisticated challenges in civil engineering, and the solutions are both counterintuitive and elegant. Wind does not push a building like a single uniform force. It creates pressure differences, turbulence, vortex shedding, and dynamic resonances that change rapidly with height, shape, and surrounding terrain. At ground level, a city's street grid slows and redirects airflow. At the 200-meter tower, wind speeds can be 3 or 4 times faster and far less predictable. The critical risk is not simply the force of the wind pushing laterally against the building. It is resonance. If wind-induced oscillations match the building's natural frequency, the structure can amplify those vibrations rather than dampening them. Engineers learned this lesson catastrophically in 1940 when the Tacoma Narrows Bridge collapsed from aerodynamic flutter at relatively modest wind speeds. Modern skyscraper design is built around preventing exactly this failure mode. The foundation itself is the first line of defense. For super tall buildings, engineers drive piles deep into bedrock, sometimes 60 to 80 meters below the surface. These concrete and steel piles transfer the building's enormous weight, but more importantly, they anchor the structure against lateral movement caused by wind. In cities built on soft soil or reclaimed land, the engineering becomes even more complex. Engineers in areas like San Francisco or Tokyo use friction piles, which grip the surrounding soil along their entire length rather than bearing on hard rock below. Soil structure interaction models simulate how the ground itself will deflect and transmit forces during strong wind events, accounting for the nonlinear behavior of saturated clay, sand, or fill material under dynamic loading. Above the foundation, engineers address wind-induced motion with a device called a tuned mass damper. This is typically a massive concrete or steel pendulum weighing hundreds of tons, suspended high inside the building, and calibrated to oscillate at exactly the opposite frequency of the building's natural sway. Taipei 101, once the world's tallest building, has a damper weighing 730 tons that hangs between floors 87 and 92. When the building sways east, the damper swings west, partially canceling the motion. Residents on upper floors feel perhaps 30% less movement than they would without the device. The Lot World Tower in Seoul uses an active mass damper with computer-controlled actuators that push the mass in precisely the right direction at the right moment, going beyond passive cancellation to active stabilization. Perhaps the most elegant solution is to design the building's shape itself to reduce wind loads. Square towers generate powerful vortex shedding on their downwind faces, creating rhythmic pressure pulses that can induce resonance. By tapering the building as it rises, twisting the floor plates slightly with each successive level, or cutting corners and recesses into the facade, engineers dramatically reduce these vortices. The Burj Khalifa in Dubai reduces wind forces through a spiraling setback design that prevents any single vortex from traveling the full height of the building. Wind tunnel tests on scale models, and today computational fluid dynamic simulations, allow engineers to test dozens of shape variants and quantify exactly how each modification changes the aerodynamic load profile before a single meter of concrete is poured. Inside the building, the structural logic is equally sophisticated. A reinforced concrete core runs the full height of the tower, acting as a stiff spine that resists lateral forces. Around that core, outrigger trusses connect to perimeter megacolumns, transferring wind-induced tension and compression out to the building's exterior. This distributes the load across the entire footprint rather than concentrating it at the core alone. For very tall buildings, the interaction between foundation flexibility, structural stiffness, and the dynamic properties of concrete as it creeps and shrinks over decades all feed into a single integrated model. Foundation engineers, structural engineers, and geotechnical specialists work from a shared computational model that tracks how the building will behave not just on the day it opens, but 20, 50, and 100 years later. The result of all this engineering is a building that appears rigid and solid from the outside, while silently managing forces that would destroy a less sophisticated structure. The foundation, the dampers, the shape, and the internal structure all work together as a system. Designing a skyscraper foundation to handle wind is not about making the building resist movement. It is about designing exactly the right amount and kind of movement, in exactly the right direction, so the building survives conditions that nature throws at it for centuries to come.